In today's class, we will see the last topic from second unit, that is online search agent and unknown environment. And in today's class, we will see the offline search and online search, that is the difference between online and offline searching, and online search problems, online search agent, and online local search. The difference between offline searching algorithm and online searching algorithm. First, let us see the offline search algorithms. Okay, this algorithm knows the complete solution before taking their first action. Okay, that means the algorithm is given the whole problem data. Problem data means input data. Input data from the beginning itself. Okay, and it required to output an answer which solves the problem at hand. Okay, that is, in the offline algorithm, we have to feed all the required data from the beginning itself, and it will take the actions according to the current state. Okay, so the algorithms which we have seen up to this are called as offline algorithm. In contrast, we will see the online algorithm. Online algorithm are not the algorithm that will search in computer with internet connection. Okay, this is not online algorithm, but these algorithms, that is online search algorithm, first take an action, then it observe the environment and compute the next action. Okay, and here in online algorithm, it accept only the input piece by piece. Okay, whenever it receives an input, and that input will be considered for the next action, right? And this input will be given to the computer in serial fashion. Serial fashion means one piece after another piece. Whenever the computer or the algorithm receives the input data, then that data will be considered for the next action. Okay, so it will perform action, then it will observe the environment. Okay, that is, in the order that the input is fed to the algorithm without having the entire input available from the beginning. Okay, this is called as online searching algorithm. Okay, the agent which is used in online searching are called as online search agents. Online searching is nothing but in unknown environment, the agent does not know what state exists, means the current state, and what its action do, that is the next state. So the agent does not have any knowledge about the current state as well as the next state, and the agent must use its actions, because the agent can only do actions on the environment, and these actions as experiments here, because by means of experience only it can predict the next state, isn't it? So the agent must use its actions as experiments in order to learn about the environment. Okay, because the online searching is executed in unknown environment, right? And also the online searching is suitable for dynamic environment as well as semi-dynamic environment, and it is very much helpful in non-deterministic domains. Let us see some example for online searching. Let us take one robot which is placed in a new building. Okay, let us take our famous vacuum world, that is vacuum cleaner example. This is room A and room B may be somewhere else. Now the agent want to clean both the rooms, and hence it should know the route from A and B, that is room A and room B. Okay, hence it must explore to build a map. Okay, so by using the map only it can get the way from A to B, right? So the robot, if it is placed in a new building, then it have to create a map from room A to room B. And let us take another example, that is newborn baby. The newborn baby knows many actions, but it does not know anything about the causes of those actions on the environment, right? What the action will do on the environment is absolutely unknown by this newborn baby. Okay, and by using the experience, that is, it has experience only few of the possible states it can reach. Okay, that is, by applying action on the environment and continuously it will do the same to learn that environment. Okay, and the gradual discovery of how the world is called as online search process. Okay, so the online search process will happen only by the gradual discovery, or by using the experience only the environment will be known by the robot. Online searching problem. Okay, this online searching problem solved by interleaving computation, sensing and acting. Right? And these things are very important to solve the online searching problem. Here we are having online agent. The agent knows only the following things. First one is the list of actions, action of S. Okay, a list of legal action in state S. Okay, and second one is the cost of S comma A comma S dash. Right, that means the cost of applying action A in state S to arrive state S dash. Here the suitable action, that is legal action, is nothing but A, and the S is nothing but the current state, and S dash is nothing but the new state. So the agent can compute the cost of this particular action on S to get S dash. And the third one is goal of S. That is, the agent will test whether the current state is goal state or not. That is called as goal test. Okay, and the agent cannot determine these things. This is very important in online searching. Result of S comma A. Right? What will be the result of this particular action will perform? Yes. Okay, by using experience only the agent will know these things, except by actually being in state S and doing action A. That is, after performing action A on the current state only, the agent can know which will be the next state. Okay, previously it cannot define this S of that, sorry, result of S comma A. The maze problem, this is very good example for online searching. Here the agent start at S and have to reach this G. Okay, this is the starting place and this is the goal state. Goal state. Okay, see here the agent can move anywhere else from this board. Okay, what are the actions the agent can perform in this board? It can go up, down, left and right. Okay, it can move in all the direction, but the agent cannot know anything about if it performs up, then whether it will reach this 1 comma 2. Okay, and if it performs go down, that is move down operation, it cannot go down, but it will be in the same state, that is 1 comma 1. Okay, then how this agent will reach to the goal state? Okay, so this is what the problem of online searching. The agent can know all these actions, but it cannot know if I apply a particular action on this state and how, that is what will be the next state. Okay, then how this agent of maze game will reach from starting state to goal state? Okay, by using this admissible heuristic function, that is h of s. The h of s is very much helpful to estimate the distance from one point to another point, that is one state to another state. So by using this h of s function, it can estimate the distance from current state to goal state. Okay, now the agent must use the Manhattan distance formula to compute the distance from one state to another state. Okay, here suppose if it is in the point x1 comma y1 and the next point is x2 comma y2, then what is the distance between 2 points? The determinant of x1 minus x2 plus y1 minus y2. So by using this formula, it can easily compute the distance from 2 points. For example, currently if the agent is in this place, then to reach uh, these states, okay, so by applying any one of the action, that is up, down, and this is left and this is right. Okay, see, one single action will be enough to reach these states, but to reach the diagonal state it requires two actions. So these numbers are 2. Okay, first it has to move down and go right. Okay, two actions are required. And here the objective of our online agent is to reach the goal state with the minimum cost. Okay, this is what the goal of almost all the agents in searching problem. Okay, from starting state to goal state, what will be the minimum path cost? Okay, here two things are very important. First one is competitive ratio and second one is dead end. First let us see what is this competitive ratio. Here the agent compare the discovered path with the optimal path, okay, in the known environment, and this distance should be, the difference should be very small here. Okay, first the agent have to discover the route from starting state to goal state in the unknown environment. Okay, first it may go here or it may go in this place in this direction because the hurdle is here. It cannot go beyond that. Okay, after that it will slowly goes in this direction and reach the goal state. Right? This particular path cost should be very minimum difference between the original optimal path in the known environment. Okay, so this is called as competitive ratio. Competitive ratio means the difference between the discovered agent's route with the original path cost, the difference should be very minimum. And next one is dead end. So when come to dead end, the state from which no goal state is reachable, that is called as dead end. Okay, for example, if the agent moves to this particular place, the agent never reach the goal state beyond this particular route. Okay, so it has to come back to its original state and it have to take another route. Okay, and no algorithm can avoid this dead end in all state spaces. Here these two are identical state space diagram, and the two state space that might leads to online search agent to a dead end. Okay, suppose if the agent takes this particular state, definitely it will reach the dead end, and when come to here, if the agent takes this particular action, then it will again reach to dead end. Okay, so the algorithm can visit only the state, but it does not tell about whether it is top state or bottom state. Okay, so this is online because the environment is completely unknown by the agent. And this is another diagram. Here this is the starting state and this is the goal state. Okay, see, from this starting state to goal state, okay, there are n number of thin and long walls. Hence, it is very difficult for this online agent to find the best route from starting state to goal state. Okay, of course, the route will be inefficient route, because if this agent discovers any of the route, immediately there is another wall in between that route path cost. Okay, hence sometimes it can find the route like this. If it goes like that, then definitely the route will be very inefficient when compared to the original path. In online searching problem, two things are important. First one is dead end and second one is safely explorable. When come to dead end, from a particular action we will reach some of the state, and from this particular state we cannot reach the goal state. Goal state may be somewhere else. Okay, so if the agent reaches this particular state, and this is called as dead end. Dead end means there is no way to return to the previous state. Okay, from once we reach this particular state, we cannot return back to this original state. Okay, so this is called as dead end. For example, in robot exploration, if the robot moves on stairs, that is staircase, ramp, cliff and one-way street, then it cannot come back to its original place. Hence, this is called as dead end. Dead end means from this particular node we cannot reach the goal. And second one is safely explorable, that is sum of goal state is reachable from every reachable state. Okay, so here this may be the goal and this may be the starting state. So from all the state the goal is reachable. Okay, for example, the maze problem, 8 puzzle problem and 8 queens problem, all are safely explorable problems. Online search agents. Here these agents know about the list of actions. Okay, so in this state S, the agent can perform some of the action, okay, so that it can reach S dash, next action. Okay, see, when it moves to next state, that is S state, it can observe the environment, okay, by using the perception, that is by using sensor it can observe the environment, and then only it knows about where it reached now. Okay, so this is called as online agent. So from this information it can expand its map of the environment. Okay, from this state what action we need to perform to reach the next action, from here which action we need to select to reach next state. Okay, likewise it can expand the map of the environment and update every action. After every action the map will be updated. Okay, so in online algorithm it can discover the successor only for the state that it physically occupied. Okay, see, it can observe the S dash only it physically reach this particular state. Okay, and the next node expand is child of the previous node. Okay, see, if we reach this particular state, then this will become child and this will become parent. Online depth first exploration agent. Okay, here the agent stores its map. Okay, so that maps is used to find the path from starting state to goal state. Okay, so to explore this particular map, the agent maintains a table called result table. Okay, here it records the state resulting from executing action A in state S. Okay, so suppose if it performs any of the action in this particular state, which state it will reach, that is S dash. This S dash will be stored in a table, right? So here the difficulty is the agent, suppose if a agent having 4 actions, then all the 4 actions should be tried in this same, this is 3, okay, the same S. Okay, then it will reach S dash 1, S dash 2, S dash 3, S dash 4. Okay, so how it will know about this S dash 1? once it physically reach this particular state, then only it knows something about this S dash 1. Okay, likewise it have to try all the possible actions on the single node or single state. So this is what the difficulty in this online agent. Okay, and second, it will maintain another table to avoid dead end. That is, for each state, that is the parent state to which the agent has not yet backtracked. Okay, for example, so this is goal and this is deadlock. Okay, so the agent have to keep track of this particular state, okay, from which it can backtrack. Okay, suppose if it reach this dead end, immediately it come back up to this particular state only and it will take another route. Okay, so that it can easily reach the goal. So this will be maintained by another table, okay, to avoid dead end. So these two are important tables maintained by online agent. In this online depth first exploration, the agent just keep one current state in memory, only one current state in memory, and it can do random walk to explore the environment. So this is online depth first exploration. But when come to here, the random walk is not randomly selected any of the state, instead of randomly select any one of the available action. This is important. Okay, so it cannot restart randomly at every iteration, but it will randomly select any one of the available action from the current state. Right, here the preference can be given to actions which are not yet tried. Okay, when come to next state, it will try another action to get the new state. Okay, and this process will continue until it finds a goal or completes its exploration. Okay, until it finds a goal in the environment or it completes the exploration of this current environment. Right. Okay, let us see the advantage of online depth first exploration. It provides the space is finite. It provides the space, that is the environment that will be finite, that is the limited one, and safely explorable until it reach the goal. Right, this is advantage. And second one is drawback. This process will take very long time to find its goal. Okay, this is only the drawback of online depth first exploration. Okay, in this online depth first exploration, the environment in which random walk will take exponentially many steps to find the goal. Okay, let us take this diagram here. The starting node is S and goal node is G. See, from the starting node, it will take the forward means forward step. There is no backward step at the state S. But all the other nodes in this top row are having two backward steps. See, from here, one backward step is here, another backward step is here. Because we are randomly select the actions, random action sometimes leads to backward direction. Okay, so this process will take long time when compared to all the other process. That is, for each state in top row S, that is except S, backward process is twice as likely forward process. Okay, here we are having only forward process. Instead of the another forward process, the random action will select the sometimes backward direction. Learning real-time A-star search algorithm, that is LRTA search algorithm. This algorithm builds a map of the environment in the result table. Okay, here it updates the cost estimate for the state it just left. Okay, for example, currently the agent is in state S and it will perform some of the action, that is random action, to reach state S dash. Okay, once it reaches state S dash, then it updates the cost estimate of the previous state. Right, and this is denoted as h of s. Okay, here the action not yet tried in the state. Okay, some of the action are already tried, but some of the actions may not be tried up to this, and these actions always assumed to lead the goal immediately. Okay, with the least possible cost. That means, see, we are in state S and we can randomly select some of the actions A1 to reach S dash 1 and A to reach S dash 2 and A3 is S dash 3. Okay, A2, A3. And if it does not leads towards the goal, then the agent assumes that the actions not yet been tried in the state, in this particular state, always assumed to lead immediately to the goal. Suppose if I didn't try some of the action AN, now it assumes that this AN leads towards the goal with the least possible cost. Okay, and this optimism under uncertainty encourages the agent to explore new possible promising path. This diagram shows 5 iteration of LRTA search algorithm in one dimensional state space. Okay, the dimension of searching is only a single direction. Okay, that is one dimensional search space, and each state is labeled with h of s. Okay, each state it is having a label, it defines the h, that is heuristic value of this particular state. What is heuristic value? The assumed cost to reach the goal. Okay, and the current cost estimate to reach a goal, and every link has action cost of 1. See, every link the action cost is 1 for forward direction as well as backward direction, and the red mark the location of the agent. See, these are the location of agent on every iteration, and updated cost estimate at each iteration have doubled the circle. Okay, suppose this is the first iteration. In the first iteration the agent is in this location. After that it will select this particular action to reach here. Okay, once it reach here, then the cost is previously 2 and the current cost is also 2. Then what will happen? From here the cost will be of course 3. Hence it update the cost to 3. Okay, when it comes here, again it will select any of the action to reach next node. Once it reach next node, the cost is, that is estimation cost is 4. That means from the previous it should be 5. Okay, so likewise it update the cost of the previous node. Okay, see, from here the node reach, that is the node select any one of the action to reach this particular state. From here it is 4, means from previous it of course 5, because 1 should be added here, isn't it? So from previous it should be of course 5 to reach the goal state. So far we have seen the online search agents and unknown environment from second unit, and this is the last topic from this unit, and you can expect this from 5 mark question or 10 mark question, right? From this topic we have seen offline search and online search difference, and the online search problems, online search agent and online local search. For more information please go through your textbook, and from the next class we will start our third unit. Thank you.